I will be speaking about our work on protecting low-power sensors from leaking information through adaptive sampling policies. Battery-powered devices provide a cheap method for performing widespread data collection. And these systems have applications in areas such as activity recognition and agriculture monitoring. In this work, we consider a standard sensing model where devices periodically capture measurements over time before sending these measurements over a wireless link to a centralized server. There are a few key considerations we must make when designing sensing systems. The first is that sensors often monitor private events, and devices have to take care to maintain this data privacy and avoid unwanted information leakage. A second is that sensors often operate under finite energy constraints, in which case they must carefully manage their energy consumption. One technique that devices use to save energy is to batch measurements and send these readings at periodic intervals. This technique of batching helps save energy by reducing the amount of time power-hungry radio modules must spend in active mode. While this technique of batching is useful, it's often not sufficient to guarantee that systems meet energy constraints, and applications often require greater control. One further technique we can use to save energy is that of data sampling. Subsampling is able to lead to energy savings through a reduction in sensing, as well as the subsequent computation and communication. Data sampling, however, comes at a trade-off, and that trade-off is in terms of error. As the system decreases its collection rate, it reduces its energy consumption, but also displays a higher reconstruction error, as the sensor provides a less complete view of its underlying environment. With this trade-off, we have the systems level goal of designing sampling policies that can minimize their reconstruction error, while also meeting any desired energy constraints. Now, one consideration we must make when designing sampling policies is that the number of captured elements in each batch window determines the size of the messages transmitted between sensor and server. So returning to our system model, we have that sensor devices periodically send encrypted measurement batches. We can consider an attacker who passively monitors this wireless link. And if the sensor device displays any variance in its message sizes, then the attacker can potentially use this variance to infer a potentially private sensed event. Note that this inference is possible even in the face of data encryption, because message sizes form a potential side channel. Thus, to ensure data privacy, we must design sampling policies to avoid any meaningful links between message sizes and data measurements. Otherwise, we run the risk of information leakage. With these properties, we therefore want to design sampling techniques that can achieve low reconstruction error, but also achieve low energy overhead and no data leakage, where these last two properties are critical on low power embedded systems. One family of techniques that attempts to address these properties is that of data-dependent adaptive sampling. Adaptive sampling is able to achieve low reconstruction error, as it sets its collection rate based on trends in previously collected values. To see why this is beneficial, we can take an example of accelerometer values sampled over time. Using an adaptive policy based on linear comparisons, we have that adaptation allows us to collect very few elements on a relatively constant sequence, allocating more of the budget to the highly variable sequence below. In essence, the system can allocate the available sample rate based on sequence variance to achieve a low reconstruction error in total. Now, the downside of adaptive sampling comes from the perspective of data privacy, namely that if the system captures a few elements, we can infer that the underlying subject was walking. In contrast, if the system captures more elements, the underlying subject was likely running. Note that this form of data leakage actually occurs for multiple different adaptive policies, and it also occurs for the same adaptive policy across multiple different tasks, as we will see in future slides. Thus, the issue with adaptive sampling isn't necessarily due to a single algorithm or task. It instead is more fundamental to the data-driven behavior of the underlying technique. Thus, we have that adaptive sampling is able to meet energy constraints and also achieve low system error, but does so at the cost of data privacy. Now, one method we can use to try to address this privacy problem is to avoid using data-dependent information in the collection pattern. And what we'd get here is a technique similar to random sampling. Returning to our previous example, random sampling will always collect the same number of elements on each window. This is beneficial from the perspective of privacy because an attacker who's simply observing this collection rate cannot use the collection rate to infer any information about the underlying events. Now, the problem with random sampling comes from the perspective of reconstruction error. Namely, if we compare random sampling to what is achievable with adaptive sampling, we find that adaptive sampling achieves lower error on average, despite actually capturing fewer elements in this example in total. Thus, what we have with random sampling is that it's able to manage energy consumption and also achieve perfect data privacy, but it does so at the cost of additional error. An alternative approach we can take to try to address the problem with adaptive sampling is that of message padding. As a whole, message padding adds extra bytes to hide the collection rate employed by the adaptive policy, where every single batch is padded up to the largest possible size. The issue with this approach, however, is that it's far too expensive on low-power devices due to the high energy cost of wireless communication. Namely, if we had the energy to spend on padding up messages, then we could potentially just capture more elements in an underlying sampling policy. In essence, what we have with message padding is that it's able to achieve perfect data privacy through these fixed length messages, and it also achieves good error due to the underlying adaptive policy. The issue is that it achieves high overhead in terms of energy based on this additional communication. What we have is that these existing approaches tend to compromise on at least one of data privacy, sampling error, or energy consumption. What we'd like to do is design a system that achieves perfect privacy and energy consumption, but achieves an error that's close to that of adaptive sampling. And to achieve this trade-off, we introduce a new framework in this work called adaptive group encoding. Adaptive group encoding creates fixed length messages, thereby standardizing communication patterns. The way it does this is for any collected batch, it applies a lossy encoding technique. Adaptive group encoding works as a post-processing step for any periodic adaptive sampling policy and right before any encryption algorithm. The idea behind this approach is to maintain generality and really work as a drop-in step in existing applications. To provide a general solution, the system actually cannot make many assumptions about trends in the policy's collection rates or even distributions of the underlying data. The only real assumption adaptive group encoding makes is that the sensor captures fixed point numerical measurements, which is already a standard practice. The key idea behind adaptive group encoding is that it compresses oversampled batches and expands undersampled windows. What this allows us to do is set the target fixed length message size to be far smaller than what we would normally see with standard message padding. In particular, we can set this target message size to be the average message length of the original adaptive policy. What this means is that adaptive group encoding incurs negligible overhead in comparison in terms of bandwidth, and by extension, in terms of energy. Now, the key property of adaptive group encoding is how it goes about compressing larger batches into smaller messages. Because the system makes no assumptions about data distributions, it has to guarantee compression ratios for potentially arbitrary data. This is impossible to do through a strictly lossless approach. So adaptive group encoding has to take a lossy method. The way we do this is through fixed point quantization. Adaptive group encoding sets bit widths of individual measurements and applies quantization such that the resulting message will be at most the target message size. Now, quantization alone often leads to unnecessary errors due to this compression technique. These errors generally stem from the use of a uniform number of fractional bits, and they're especially pronounced on examples with small bit widths. Namely, if we're trying to quantize measurements to 3 bits of magnitude, we can take 2 different measurements here, 1.5 and 1/8. With these 3 bits, we can actually represent both measurements with 100% faithfulness if we allow the binary point to move. Using a fixed binary point across both measurements would require at least some data loss. Now, this use of a moving binary point is essentially just floating point encoding. And the challenge with it is that attaching an exponent value to every single measurement requires a significant number of bits, which is not always possible to include, especially when trying to achieve high compression ratios. Thus, to solve this problem, we instead apply run length encoding to these exponents, which compresses these values. And this procedure takes advantage of temporal relationships that are often present in sensor measurements. What this run length encoding provides are groups of consecutive measurements that have the same exponent value. Within each group, we only have to store the exponent once, leading to space savings. Now, the problem with run length encoding is that it itself provides no guarantees on its compression ratios. And as adaptive group encoding doesn't make assumptions about relationships in the data, we cannot guarantee that run length encoding will actually lead to compression at all. Thus, adaptive group encoding must handle cases where run length encoding does not provide adequate compression. The way we do this is through a lossy technique, where adaptive group encoding places a cap on the number of exponent groups, and it'll actually merge these adjacent groups with similar exponents in order to enforce this limit. What we get with this process is the ability to encode as much exponent information as possible while limiting the amount of space overhead that this information requires. From these groups, adaptive group encoding assigns a bit width and quantizes values in each group corresponding to this width. Working in these smaller multiples actually helps the system utilize the entire target message size, therefore creating a more accurate system. Now, adaptive group encoding is based on building blocks from quantization. And I think it's worth highlighting the benefit of this approach. Namely, these building blocks allow us to create an extremely efficient system, which is massively beneficial when executing on resource-constrained embedded devices. Adaptive group encoding aims to be a drop-in step for existing applications, and it's critical that it maintains low overhead as a result. We evaluate the adaptive group encoding system across 11 different energy constraints along 2 different dimensions, the first being measurement error, and the second being information leakage, which is shown on the next slide. In terms of measurement error, what we find is that adaptive group encoding achieves lower error than baseline systems that show no information leakage, in this case, random sampling and message padding, where this message padding shows high error due to frequent budget violations. Furthermore, adaptive group encoding achieves an error that's actually relatively close to adaptive sampling, allowing the system to preserve as much of adaptive sampling's low error as possible. Now, to confirm this limited information leakage, we can observe the mutual information between sensed events and message sizes. What we find is that standard adaptive sampling shows highly non-zero mutual information across multiple different independent tasks. This indicates a distinct relationship between message sizes and sensed events, which is an indicator of information leakage. In contrast, adaptive group encoding, which uses this same adaptive policy underneath, completely eliminates this leakage and shows zero mutual information as a result. To further highlight this leakage, we can consider a practical attacker who uses a decision tree model, which takes in message sizes and predicts sense events. What we find is that when attacking standard adaptive sampling, the adversary can achieve over 2 times more accuracy in many cases than the most frequent result on any individual task. In contrast, adaptive group encoding always guarantees this most frequent result because it shows no variance in its message sizes. To conclude, what we've talked about here is how data-driven adaptive sampling links its collection pattern to information about sensed events in the underlying data. This presents a problem from the perspective of data privacy because sensors leak these collection rates through the size of periodic batched messages. To fix this problem, we propose an alternative approach called adaptive group encoding, which creates fixed-length messages, thereby standardizing communication patterns by applying a lossy encoding technique to compress over sampled sequences. As a result, adaptive group encoding is able to achieve lower reconstruction error than existing techniques that also prevent information leakage in this setting. Adaptive group encoding takes care to provide negligible energy and bandwidth overhead, making it a security solution suitable for low-power systems.